Welcome back. This is the second video of section 5.2 in which I'm going to prove the first version of the inverse function theorem or the local inversion theorem. Okay, so as we explained earlier, this is our plan. It has 4 steps. So let us carry out this program. For y in f, we set psi sub y of x is just x minus the inverse of the derivative at a in the direction y minus f of x. Now, since the derivative, so f prime of a minus 1 is an isomorphism, so it's a bijection, we see that the equation y equal f of x that I want to solve locally is equivalent to the fixed point of psi y. Okay, so if psi y of x equal x, then this is 0, and therefore y minus f of x is 0. If y minus f of x is 0, then psi y of x is equal to x. Okay, so I reduced my problem to a fixed point problem. Okay, and now I have an important tool, which is the Banach fixed point theorem, to prove that psi sub y has a fixed point. But in general, we have to restrict y to a neighborhood of b, because in general, psi sub y need not have a fixed point in general if y is not restricted. Okay. However, psi sub y is always a contraction. Okay, but restricting y to vary in a neighborhood of b will dictate that psi sub y maps a closed ball into itself, and then you could apply the fixed point, the Banach fixed point theorem. Okay. So let us choose this restriction first. Since f prime is continuous at a by assumption, then f prime of a minus f prime of zeta is less than any number. So I take the number here less than 1 over twice this norm for every zeta in some ball of center A and radius alpha. Okay, this is just continuity of f prime at A. Now, choose 2 points, x and x prime, in this closed ball of center A and radius alpha. And for t in 0, 1, consider this function from 0, 1 to the space E, given by this convex combination of x and x prime minus the inverse of the derivative at A in the direction f of this convex combination. Okay, this makes sense actually because this ball is convex, so this convex combination is in the ball as well. Okay, and this ball is contained in U. This closed ball is contained in U. Now, if we set t equal 1, we get u1 of x equal to x. This is 0. F prime a minus 1, and this becomes x, so f of x, simply. When I put t equals 0, I get x prime minus same thing, but with x prime. Okay. Now, by the chain rule, if we differentiate with respect to t, the derivative of this term is just x. The derivative of this term is minus x prime. And now, this is a linear bounded map, so its derivative is just itself. And the derivative of this guy, again by the chain rule, is f prime of the convex combination times the derivative of what is inside, which is just x minus x prime. And I can rewrite this in this way. F prime a minus 1, which is evaluated at f prime of a, x minus x prime, minus f prime of the convex combination x minus x prime. Okay, so this is the composition of maps. Okay, because f prime minus 1, f prime of a is just the identity. Okay. And now I use the operator norm. So the norm of the derivative is less than the operator of the inverse of f prime of a times the difference between f prime of A and f prime of this convex combination times the norm of x minus x prime. Okay. And by our choice of alpha, if alpha is so since x and x prime are both in the closed ball of center A and radius alpha, then this convex combination is in the ball. So according to our definition, this quantity is less than 1 over twice this norm. So this product is less than 1/2. Okay, so this is, you take this to be zeta if you like. Okay, and now by the mean value theorem 3.3, u1 minus u0 is less or equal than 1/2 times 1 minus 0. But if you recall the formula for u1 and u0, you will get x minus, so u1 is just x minus f prime a minus 1 f of x, and u0 is just x prime minus the similar quantity. Okay, now if I replace, if I add and subtract f prime a minus 1 of y, then this term here is just psi y of x minus psi y of x prime. Just add y here if you like. So I get that psi sub y is a contraction for every y, actually, no restriction on y. Okay. But cannot apply yet the fixed point problem, the fixed point theorem, because we don't know that psi maps the ball into itself, a closed ball into itself. Okay, so this is what we are going to do. We choose beta to be alpha over twice the norm of the inverse of f prime of A, so that when I multiply by this norm, I get alpha over 2. Okay, and this so now when we restrict y to the closed ball of center B and radius beta, then psi sub y maps the closed ball of center A and radius alpha into itself. So I have a self map, which is a contraction. Okay, this is not difficult. Take x in this closed ball and use the triangle inequality. So we want to prove that psi y of x is in this ball. So the distance to the center is less than alpha. So I want to prove that this is less than alpha. So I use the triangle inequality and I add and subtract psi sub y of A. Okay, so since psi y is a 1/2 contraction, this first term is less than 1/2 x minus A. And if you go back to the definition of psi y of x is x minus the inverse of the derivative y minus f of x. So psi y of A is just A minus this quantity. So we just get f prime of A minus 1 times y minus f of A, which is B. Okay, so in all this discussion, B is f of A. And now I apply the operator norm to this guy. And if y is in this ball, then y minus b in norm is less than beta. So this is less or equal than beta. Beta times this constant is equal to alpha over 2. So this second term is less or equal than alpha over 2. And I get that psi y of x minus a in norm is less or equal than alpha. And this proves that psi y of x is in the closed ball of center A and radius alpha. So I proved the claim. So now I have all the ingredients to apply the Banach fixed point theorem. I have a contraction from a closed set in a complete space, which is complete. And therefore, for every y, we have a fixed point of psi y of psi y. Okay? So for every y in this ball, in the neighborhood of B, there exists a unique x in the closed ball of center A and radius alpha that solves the fixed point problem and therefore solves the equation. Okay. So therefore I have a map now that I call G. So I have a map G from the closed ball of center B and radius beta in F into the closed ball of center A and radius alpha in E, that to each y associates the unique solution of this equation. So I solve this equation locally. Okay, so what did I prove? I proved that whenever y equal to f of x and y is in this ball, if x, uniqueness tells me that if x is in this ball of center A and radius alpha, then it's necessarily unique. Okay? So since g of b equal a, so since b is in the closed ball of center B and radius beta, and a is in the closed ball of center A and radius alpha, then uniqueness tells me that g of b equal to a. Okay. So now we have to be careful a little bit here. So by definition, first, f of g of y is equal to y whenever y is restricted to this neighborhood, closed neighborhood. Okay, this is what I called w bar. Now, I cannot conclude that f maps the closed ball of center A alpha into the closed ball of center B and radius beta, or even that f is injective. Okay, nothing in the assumptions tell me that. So we have to, in order to get a bijection, I need to restrict f to a smaller domain. Okay, because so if f maps this ball into this ball, then f must be very rigid. Okay, so it must be kind of rotation or translations and homothéties, but f is very general here. Okay, so in general, f, the image of under f of this ball contains this ball. So but essentially, when I restrict properly x and y, then g is the inverse of f because of this equation. Okay. So uniqueness of the fixed point tells me, this is what I was saying before, is that if I know that x and x prime are close enough to a in the ball of center A and radius alpha, and f of x equal f of x prime, then, and this common value belongs to the ball of center B and the radius beta, then necessarily x equal x prime. Okay, this is the uniqueness of the fixed point. Okay, in general, if f of x equal f of x prime without any restriction, I cannot conclude that x equal x prime. But here, when I restrict x and x prime to this closed ball, and I know that the common value is close enough to b, then I deduce that x equal x prime. Okay. So this is why g of b equal a. Actually, we can draw a figure to understand better what's happening. So draw a ball of center A and a ball of center B. The image of the first ball could be something very strange, not necessarily a ball. Okay, so and the inverse under G of B prime need not contain B prime of A and alpha. Okay, so a picture may help you understand what's happening. And we get back to this later. Okay, now step 3, I prove that this map G, which is well defined, is Lipschitz continuous, and this is not difficult. By construction, G of y for y in the closed ball of center B and radius beta, gy is a fixed point of psi y. Okay, this is by construction. Now take two elements y and y prime in the vicinity of B, okay, in the closed ball of center B and radius beta. Now, if you go back to the definition of psi y of x is just x plus f prime of a minus 1 of y minus f of x. So just replace x by its value. And f of g of y prime by construction just y prime, as you observed. This is first thing. And what about psi y prime of g of y prime? Same thing. It's g of y prime, the argument here, plus the inverse of the derivative times y prime, this y prime comes from here, minus f of g of y prime. And this is again y prime. So I get y prime minus y prime. So this is 0, and therefore I get g of y prime. So when I do the difference between these two guys, this minus this, I cancel, these two guys cancel, and we are just left with the inverse of the derivative in the direction y minus y prime. Okay. This is the parenthesis should be outside. Okay, therefore, g of y minus g of y prime in norm, since gy and gy prime are fixed point of the corresponding psi y. So I get psi y of g of y minus psi y prime of g of y prime. So this is equal to this, and this is equal to this. And according to what we said, this is just so I use the triangle inequality because I add and subtract psi y of g of y prime. Okay. What about the first term? Psi y is a 1/2 contraction. So the first term is less than 1/2 times the distance between the arguments. The second term, according to what we said, is just the norm of this guy, which is by the operator norming inequality, is less than the norm of the operator times the norm of y minus y prime. And now we are almost done because I just use my choice of beta. So I subtract 1/2, I get 1/2 of gy minus gy prime is less than this guy. So gy minus gy prime in norm is less than twice this guy. Okay, so this proves that g is a contraction, not a contraction, it's Lipschitz continuous with constant 2 times the norm of f prime of a minus. And this is important actually because this estimate tells me that if y, so if I replace y prime by b, I get g of y minus a minus g of b, which is a, is less than this constant times beta, and this is alpha. Okay, so if y is in the open ball of center B and the radius beta, then g of y is in the open ball of center A and the radius alpha. So not only g maps, so g has two properties. It maps the closed ball into the corresponding closed ball and the open ball into the corresponding closed ball. Okay. Note that I didn't have this estimate. This estimate resembles the estimate of lemma 5.1. But in that lemma, I didn't have that G is a Lipschitz continuous. Okay, so this is the difference. So here, I take beta to be alpha divided by twice the norm of the inverse operator. Okay, but in lemma 5.1, I took alpha and beta, or alpha and delta in that case, to be the moduli of continuity of G. Okay, so this concludes step 3, and now we just have to conclude. As we said, we have to restrict f to a set smaller than the open ball BA alpha. So I take W to be this open ball of center B and radius beta, and B to be the intersection between the inverse image of W, this guy, intersected with the open ball. So here, a figure may help you understand what's happening. So we have a ball, BA alpha, another ball, BB beta. The direct image of BA alpha may be bigger than B beta, and the direct image of BB beta it's not necessarily included in BA alpha, so we have to take the intersection. Okay, and now we claim that V is open, F maps V into W, so f of V is W, and F restricted to V is injective. Okay, therefore it's injective and surjective, so it's a bijection. It's continuous because F is differentiable, and its inverse is necessarily G. Okay, because of the relation f of g of y equal y. Okay, so I leave this to you as an exercise to check the details. Okay, therefore now we are in the condition of applying lemma 5.1. So I know now that f is a bijection. I didn't know that, actually. I didn't assume that in the statement of the theorem. Okay, so the conclusion of this theorem is actually the assumption of lemma 5.1. So I can apply lemma 5.1 that, so actually this is conclusion 1 actually, and conclusion 2 is just follows from lemma 5.1 because I know that F is a homomorphism, so G is continuous. Okay, so this concludes the proof of the first version of the local inversion theorem. Okay, I will stop here and draw some consequences of this important theorem in the next video. So thank you for attention.